Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. Flattening the Network introduces a modernized approach to network design that emphasizes speed, simplicity, and scalability. In contrast to legacy hierarchical networks, spine and leaf architecture minimizes latency, eliminates unnecessary hops, and offers predictable performance across all endpoints. This model has become a fundamental design in high-performance data centers, especially in environments that rely on virtual machines, containers, and large-scale distributed services. With its emphasis on equal path distances and high availability, this architecture provides a framework that meets the demands of today's east-west, traffic-heavy workloads. On the Network Plus exam, candidates are expected to understand the functional layout of spine and leaf, its differences from three-tier architectures, and the advantages it offers for scalable and fault-tolerant design. Questions may focus on identifying diagrams, explaining routing behavior, or selecting the best model for high-density environments. The exam may also include scenarios where traffic flow, redundancy, or performance must be evaluated across different topologies. Recognizing how spine and leaf supports these objectives is critical to performing well on questions related to architecture and infrastructure. The spine and leaf topology consists of just two switch layers, spine switches and leaf switches. Each leaf switch connects to every spine switch in a full mesh, forming a non-blocking, highly redundant network. Leaf switches serve as the point of connection for servers, storage systems, and other endpoint devices, while spine switches act as the high-speed aggregation layer that moves traffic between leaf switches. There are no direct connections between leaf switches or between spine switches. Every packet that moves from one endpoint to another travels up to a spine and then back down to the destination leaf. Spine switches are designed for raw speed and capacity. These devices connect to every leaf switch, but do not connect to endpoints like servers or firewalls. Their role is to serve as an intelligent transit layer that ensures all leaf switches can communicate with one another with equal performance. Since every leaf has an uplink to every spine, no single spine becomes a bottleneck. This balanced distribution of traffic allows for predictable latency and efficient utilization of every available uplink, particularly when routing protocols support load-balanced multipath routing. Leaf switches function as the access layer for all endpoints in the data center, whether connecting physical servers, virtual hosts, storage arrays, or other infrastructure components. All endpoint devices plug into leaf switches. These switches then relay traffic upward to the spine layer. Every leaf switch has the same role and the same number of spine connections, which standardizes the access layer and simplifies both deployment and maintenance. This equal role model allows devices anywhere in the fabric to reach any other device in just 2 hops. The result of this 2-layer configuration is a flat topology that contrasts sharply with traditional hierarchical models. In a 3-tier network, traffic may pass from an access switch to a distribution switch and then up to a core router before reaching its destination. Each of these hops adds delay and creates points of congestion or failure. Spine and leaf flattens the architecture, eliminating the distribution layer entirely. This change reduces complexity, increases speed, and makes it easier to maintain uniform behavior across the network. Understanding the difference between east-west and north-south traffic is essential when studying spine and leaf architecture. North-south traffic moves in and out of the data center, such as from a user's computer to a hosted server, while east-west traffic moves laterally within the data center between internal systems. Legacy architectures were built with north-south traffic in mind, often introducing inefficiencies for lateral communication. Spine and leaf is optimized for east-west traffic, which now dominates modern networks due to virtualization, microservices, and internal application dependencies. Equal cost multipath routing, or ECMP, plays a vital role in maximizing performance in spine and leaf networks. With multiple equal-length paths between any 2 endpoints, ECMP allows the routing protocol to balance traffic across all available spine switches. This increases bandwidth utilization and provides immediate redundancy. If a spine switch or uplink fails, the The routing protocol simply redistributes traffic among the remaining paths without introducing delays or reconfiguration. ECMP is supported by many protocols, including OSPF and BGP, and is a standard feature in spine and leaf implementations. Spine and leaf architecture offers several advantages over traditional three-tier designs. In a three-tier model, scaling requires adding more layers or redesigning distribution blocks, which can be disruptive and complex. Spine and leaf scales linearly. More leaf switches add endpoint capacity, while more spine switches add bandwidth and redundancy. This modular scalability allows administrators to grow the network without redesigning it. Additionally, by eliminating distribution layer decision-making, the architecture reduces protocol overhead and accelerates convergence during topology changes. Physical design is a significant consideration in spine and leaf networks. Because every leaf must connect to every spine, the number of uplinks grows quickly. For example, a network with 8 spine switches and 20 leaf switches requires 160 uplinks. This dense cabling requires structured cable management, accurate labeling, and thoughtful rack layouts to prevent airflow blockages and installation errors. Many data centers use pre-terminated cable harnesses, colored patch cords, and cable trays to manage the increased complexity. While cabling density is a challenge, the performance payoff is considerable. Spine and leaf is well suited for modern use cases where consistency, performance, and reliability are non-negotiable. It excels in data centers that host virtualized environments, large-scale applications, or container orchestration platforms like Kubernetes. These systems rely on frequent and rapid east-west communication between nodes, containers, or services because every endpoint in a spine and leaf network experiences the same latency and hop count to any other endpoint. Applications behave more predictably, and performance troubleshooting becomes more straightforward. For more cyber content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. Scaling a spine and leaf architecture is straightforward and predictable, making it one of the most flexible designs for growing data center environments. To increase capacity for endpoints, more leaf switches are added and connected to all spine switches. To increase overall bandwidth across the fabric, additional spine switches can be added with each leaf then connecting to those new spines. This dual scaling strategy ensures that every path remains 2 hops, maintaining the consistent latency and performance that defines this topology. Unlike traditional networks that require significant planning to add a new layer or restructure an existing one, spine and leaf allows incremental and modular growth with minimal disruption. Routing behavior in spine and leaf designs is intentionally simple. Leaf switches maintain equal cost routes to all spine switches, which act solely as transit points. Spine switches do not perform complex decision-making or traffic filtering. They simply forward packets between leaves. This separation of roles leads to efficient traffic handling and rapid convergence during failure recovery. Routing protocols such as OSPF or BGP can be used to advertise loop-free paths and ensure that if one link or switch fails, traffic is seamlessly redirected across remaining paths without manual intervention. Spine and leaf networks support both VLANs and advanced overlays like VXLAN. While VLANs provide Layer 2 segmentation, they can become difficult to scale across multiple access points. VXLAN extends Layer 2 functionality over Layer 3 infrastructure, allowing large-scale multi-tenant environments to function with the flexibility of flat networks. In a spine and leaf design, VXLAN allows virtual machines, containers, or workloads to migrate freely across different racks or pods while maintaining the same logical network identity. This overlay model supports agile operations and cloud-like flexibility. Software-defined networking enhances the power of spine and leaf by introducing a centralized control layer that manages flow behavior, security policies, and performance optimization. SDN controllers have full visibility into the leaf and spine switches and can dynamically program the data paths based on changing application needs. The uniformity of spine and leaf's design makes it an ideal candidate for SDN orchestration, as policy enforcement and traffic redirection can be performed consistently regardless of device location. This combination supports intent-based networking and accelerates deployment times for new services. High availability is a built-in advantage of the spine and leaf model. Since every leaf switch connects to every spine switch, and most devices are dual-homed to different leafs, there is no single point of failure. If a spine switch goes offline, traffic automatically reroutes through other available spines. If a leaf switch fails, only the devices connected to that particular leaf are affected. Redundancy is achieved through physical path diversity and equal-cost routing, making this architecture resilient to hardware failures, link interruptions, or congestion spikes. Vendors including Cisco, Arista, and Juniper offer spine and leaf-ready hardware and software platforms that support advanced automation and analytics. Cisco integrates spine and leaf into its ACI fabric system, which incorporates policy-driven controls. Arista offers open standards-based switches with programmable interfaces and monitoring tools for telemetry and automation. Juniper provides its QFX line with Contrail integration supporting overlay networks and SDN frameworks. While each vendor has its own approach, the principles of equal access, deterministic routing, and horizontal scalability are consistent across all implementations. Troubleshooting spine and leaf networks is often more efficient than in hierarchical topologies because of the design's regularity and symmetry. Since every path involves only 2 hops, one up to a spine and one down to another leaf, network behavior is easy to map and predict. Diagnostic tools can check link health, monitor equal-cost multipath routing distribution, and validate flow visibility across the fabric. Issues such as asymmetric routing, underutilized links, or failed interfaces can be quickly pinpointed and resolved by observing flow patterns or comparing actual traffic behavior against expected topology. The Network Plus exam may include questions that ask you to identify the structure of a spine and leaf layout from a diagram or describe how east-west traffic is optimized in such a network. Other questions may test your understanding of ECMP routing, fault tolerance, or scalability compared to a 3-tier model. It is important to recognize the distinct roles of leaf and spine switches, the advantages of 2-hop transit, and the scenarios where this model is preferred. Mastery of these ideas supports broader concepts like network segmentation, high availability, and application-aware routing. Spine and leaf architecture is more than a buzzword. It is the blueprint for modern networks that demand speed, reliability, and adaptability. Whether you are working in a private data center, a cloud-hosted platform, or a hybrid deployment, this design supports the kind of dynamic, high-throughput environments that define today's enterprise workloads. With uniform traffic paths, predictable scaling, and seamless support for overlays and automation, Spine and Leaf offers a physical foundation for the next generation of software-defined, service-centric networking. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.